light microscope uses light as its source of radiation. Through a series of glass lenses, the light produces a magnified image of the specimen. This is a photograph of the kidney, taken at 1000 times magnification using a light microscope. This is the maximum useful magnification achievable with this system. Cells of different shapes and sizes can be seen, but little cellular detail is visible. The transmission electron microscope is capable of much greater magnification, up to 1 million times, and has a resolving power of about 200 times greater than the light microscope. This is achieved by using a high velocity beam of electrons instead of light to produce an image. At the top of a tall evacuated column is an electron gun that sends a beam of electrons through the specimen. Electrons pass through the specimen and are focused using electromagnetic lenses onto a fluorescent screen. When electrons impinge on the screen, secondary light rays are emitted and form an image. The resulting image is seen through a window at the bottom of the column. Here is an electron micrograph of cells in the kidney, magnified 10,000 times, showing much more detail on the previous light micrograph. There is a well-defined series of steps in preparing biological specimens for electron microscopy. These are fixation, dehydration, embedding, sectioning, and staining. Fixation is the first step in tissue preparation. It stabilizes the cellular organization. Cellular structure is best preserved if fixation occurs as close as possible to cell death. Tissue samples are cut into small pieces of about a cubic millimeter before being immersed in the fixative solution. The two most common fixatives used are glutaraldehyde and paraformaldehyde. Samples are left in fixative from 2 to 24 hours. The tissue is then washed in buffer and placed in osmium tetroxide, the post-fixative, which is particularly useful for the preservation of cell membranes. Osmium tetroxide combines with lipids to produce black, insoluble compounds. The tissue samples become blackened. The next step is dehydration, that is, the complete removal of water using increasing strengths of alcohol. Alcohol is then replaced with propylene oxide. Specimens are infiltrated initially with resin diluted with propylene oxide and eventually with 100% fresh resin. After approximately 36 hours of resin infiltration, the tissue is ready for embedding. Each piece is placed into a small rubber mold and resin is added. The mold is then placed into a 60-degree oven for 2 days to harden the resin. The block is now ready for trimming and section cutting. Since the resin is very hard, sections can only be cut using freshly fractured glass or a diamond knife. To make a glass knife, a strip of glass is clamped, scored, and broken to form a square. The square is rotated, clamped, scored again, and fractured diagonally to form 2 triangular glass knives. A small volume of water is needed at the cutting edge of the knife for cut sections to float onto so they can be easily collected. This water bath is created by making a miniature dam out of dental wax or by using a commercially available plastic attachment. Now that glass knives have been made, trimming and sectioning of the hardened resin block can start. The cutting face of the hardened block is trimmed into the shape of a trapezoid using a razor blade and a dissecting microscope. Final trimming is done using the precision controls of the ultramicrotome and a glass knife. Note that due to the tiny sizes of the block, the knife and water bath, the operator of the ultramicrotome has to use a microscope. When the full cutting face is exposed, a new knife is inserted into the ultramicrotome. The water bath filled with water and sections 0.5 microns in thickness are cut. They float onto the water bath. These sections are called survey sections. They are transferred using a thin glass rod to a drop of toluidine blue stain on a microscope slide. The slide is then dried on a hot plate and then viewed with a light microscope. Survey sections are examined with the light microscope to check the orientation and preservation of the tissue. Note the trapezoid shape of the block. Soles and structures are coloured blue with the dye, toluidine blue. This section also shows precipitation of the dye on the slide. Examination at higher power confirms good fixation of the tissue. The area of interest for electron microscopy is identified. Survey sections are too large and too thick to use in the electron microscope. Hence the block is retrimmed and to reduce the area of the cutting face. The retrimmed block is returned to the ultramicrotome and realigned. The glass knife is replaced with a diamond knife that makes cutting ultra-thin sections easier. The water bath is filled with water and the ultra-thin sections float off as they leave the knife edge. The different colours result from interference between the rays of light reflected off the upper and lower surfaces of the sections. Colours vary according to thickness. Here you can see sections of different colours and hence different thicknesses. Only the silver sections are suitable for electron microscopy. They are 80 nanometers thick. Compression in the sections is removed by using chloroform vapour. Note the colour changes as the sections stretch out. Sections are now ready to be collected onto a copper support grid. Grids are used instead of glass slides because electrons cannot penetrate glass. The grid is lowered into the water bath and the sections maneuvered onto it. The grid with the sections on it is then dried on filter paper. The final step in tissue preparation is staining. Contrast in electron microscopy is enhanced using heavy metals, for example uranium and lead. Deposits of heavy metals in a section deflect the electron beam. This area of the tissue will appear black in electron microscopy because no electrons have activated the emission of visible light from the fluorescent screen. These areas are referred to as being electron dense. Areas in the tissue lacking heavy metals allow electrons to pass through to the fluorescent screen, where they activate the emission of visible light. These areas are referred to as being electron light or electron lucent. Staining uses hazardous chemicals, and so the use of gloves and safety goggles are necessary precautions. To stain the sections, the grid is lowered onto a drop of the staining solutions. After washing, the sections are finally ready for viewing. The grid is placed into the specimen holder and then inserted into the electron microscope. The vacuum is restored. The section can be viewed either by looking at the fluorescent screen in the microscope or by viewing at the monitor. At 1000 times magnification, the mesh of the grid and cellular outline can be seen. At 10,000 times magnification, the structural detail is very clear. At 25,000 times magnification, cytoplasmic details and membranes can be seen.